this problem, we have a container filled with liquid water and air and water vapor. We have the initial conditions, initial pressure of 1 atmosphere, or about 101,000 pascals, initial temperature of 298 kelvins, and our mass of our water, our total mass of water is 1 kilogram. So then we are going to cap this container at these conditions, and then heat the container up until our final pressure is 200,000 pascals, and our moles of water vapor are 0.3 moles. And then we're looking to find what final temperature this will be at and the total volume of the container. So to solve this problem, I'm going to set up a number of relationships to connect all these variables. That way, when we go into Python, we can solve it using our code. So the first relationship I'm going to start with is the volume. So the total volume will be equal to the volume in the liquid phase plus the volume in the vapor phase. Makes sense. The volume down here plus the volume up here will equal the total volume. Similarly, the mass of the water total will be equal to the mass of the water in the liquid phase plus the mass of the water in the vapor phase. Okay, we know this, and we can actually find the mass of the water in the vapor phase using the desired amount of moles at the end. So that is our mass of water in the vapor phase will be equal to the number of moles in the vapor phase at the end over the molar mass. So we're using the definition of molar mass here to find the weight of our water in the vapor phase. Now from here, we have volume, mass. Now I'm going to make a relationship of pressure. So my final pressure will be equal to the sum of partial pressures in the container. So the sum of the pressure of the water vapor plus the sum of the pressure of air. So this can be found using Anton's equation. It's just the vapor pressure of water. So our vapor pressure of water will be equal to 10 to the A minus B over C plus our final temperature, since it's our the vapor pressure of water at the final point. So we have this. Now let's find a relationship for the partial pressure of air. So we can do this using the ideal gas law. So PV equals nRT. So from here, we'll have N, which is our moles of air, times our gas constant R, times the final pressure, over the volume of the vapor phase. All right, you can see some of the variables from our other relationships. They're starting to connect. So let's define this a little better. So the volume of the vapor phase, defined up here. So it will be the total volume minus the volume of the liquid, right? And we can figure out the volume of our liquid will be equal to the mass of water in the liquid phase over the density of water. So the density is mass over volume. It's a definition. So it'll be the mass or the density of water in liquid form. So now we have our volume of water vapor and our volume of liquid. We've linked it back to the total temperature. Now we need to find how to calculate moles of air. So we kind of need to think about it. At the beginning, we had our moles of air in the container, and it was set when we closed the container. So to find the moles of air, we're going to use the ideal gas law again. And this time we're going to use the initial conditions to calculate it. So the pressure will be the pressure that was here when we closed the container, so it'll be the initial pressure, minus the pressure of water at that initial temperature. We can find this variable the same way we found our pressure of water vapor at our final temperature using Anton's equation. And then it will be pressure times our volume. So in this case, our volume will be the volume that the liquid does not take up at the beginning. In this case, we're going to assume that there's no water vapor. So to calculate this volume, it will be our total volume minus what the water takes up at the beginning. So it'll be the total mass of water, which we were given, over the density of water to give us volume, density of liquid water. And this will all be over our gas constant times our initial temperature. All right, now we're almost finished. The last relationship we need to make to solve this problem is we are going to relate moles back to our final temperature and pressure. So we'll do that using, once again, the ideal gas law. So our moles of water vapor will be equal to the final pressure times our volume of our vapor over R times our final temperature. Now we have enough relationships here to go into Python, and we'll be able to solve this using our code. All right, so now that we have our relationship set up, we can go ahead and solve this problem using Python. So in our relationships, we use multiple different properties of water, such as the vapor pressure and the density. And so to accurately get those values, we are going to use a set of code that's already been made for us called CHE tools. So this has a bunch of different properties of lots of substances, but right now we're just going to use the water portion. So how we need to download this is we need to git clone. So this will clone the code into our hard drive and our link, which our link is right here. See, CHE tools here. We click on code. We're going to copy this link into the code, and we'll run it. That'll download in. And now we need to set the path for this. So we'll import system, and then we'll do system.path insert. And in the first column, because this will make it the fastest, we'll enter the path where we want to insert it. So in this case, it's our contents files and CHE tools. So content/CHE tools. And now we can use it. So how we're going to use this is, first we have to import it before we can use it. So after this, we'll import it. So we'll import tools. We'll import it as CHE. And now we can use it. So we'll use CHE.props to get the properties of water. And we will set this set of properties to our variable p. Right? Call that properties. And we'll go ahead and run that. Now I'm going to enter in all the initial values from the problem. So the initial temperature that we were given was 101,325. The initial temperature was 298. Our total mass of water was 1 kilogram. And then we had our desired values, so the final values that we needed to reach. So our desired pressure, I'm calling it PF desired because later we'll use our the final pressure as a different variable, and this will allow us to have a distinction. So our final pressure desired is 200,000, and then same idea, our moles of water vapor desired was 0.3. And then I'm also going to use, we're using R in the gas law, so I will put that in as well. So now how we're going to solve this problem is we're going to use our relationships inside of a function, and once we drive that function to 0, then we'll have our solution. All right, so let's start by creating a function. I'll just call it our equations, and we're going to pass a vector of our unknowns to it. So our unknowns are our final temperature and our total volume. So that unpacks V as our final temperature and total volume. Now, what we need to return are our two equations, right? We have two equations and two unknowns. So our first equation that we need to return is we want our final pressure to match our desired pressure, right? And we can't return an entire equation. We need to return an expression. So to do this, I'm just going to subtract our final pressure desired onto this other side and change this to a minus sign. So that way, when our final pressure equals our desired final pressure, this will equal 0. And then same idea, we need to use our desired moles of water vapor and set that equal to the moles of water vapor that's actually in our container. So moles of water vapor minus our moles of water vapor desired. And same idea, when this goes to 0, then we'll have reached those desired values. So now we can use our relationships and kind of connect all these variables back to our knowns. So that way we can solve this equation. So the first one I'm going to do is, if you remember, we said our final pressure was equal to the partial pressure of air plus the partial pressure of water, and our moles of water vapor will be equal to the partial pressure of water times the volume of our vapor divided by gas constant R times our final temperature. So now we have the partial pressure of water in both of those equations. So I will use our CHE tools, so I'll use the CHE tools to get the partial pressure of water. So we'll set our partial pressure of water equal to P dot the vapor pressure of water at our final temperature, right? And we still have some unknowns, right? We have a few relationships that we haven't used yet from the whiteboard, so let's keep working through this. Our next relationship will be we'll do the partial pressure of air. So the partial pressure of air, that's going to be equal to our moles of air. Remember, we found this using an ideal gas equation. So it would be moles of air times R times our final pressure divided by the volume in the vapor phase. So now I'm going to define moles of air. So this was our longer relationship that we found. So our moles of air was the pressure that the air exerts. So in this case, it'll be our initial pressure minus our pressure of water at our initial temperature. So we can't use the same variable. I'm just going to go ahead and use the PVAT method, and instead of final temperature, we'll use initial temperature, right? This will be times our the volume that it takes up, so this was the volume total, minus the total volume that the water takes up, and we assumed that there was no water vapor in the air. So our total mass of water times the total mass of water times divided by the density will give us our volume. So again, to get the density of water, we can get the density attribute of a liquid at our initial temperature. And then this will be divided by gas constant R times our initial temperature. So now that we have that relationship in, I'm going to, the one that we have left is our vapor, the volume of our vapor. So this was equal to our total volume minus the volume of our liquid. Now we need to define the volume of our liquid. So our volume of our liquid water, was equal to the mass of liquid water over the density of water at the final temperature. So again, we'll use P dot rho L for density of a liquid, and we'll do it at the final temperature. Now we need to define our mass, the mass of our liquid water. And this will be equal to the total volume of water minus the volume of the water vapor, which we can find using our desired moles of water vapor, times the molecular weight, the molecular weight of water, which is 18 times 10 to the negative 3 kilograms per meter squared. So now, if you look at it, every variable that we've used, we have defined above it. So now we have no missing pieces to kind of our puzzle. So we'll shift enter. Now that we have all our varied equations, we want to drive our returns equations to 0. So we'll do this using SciPy root. So to use it, we need to go in and import it. So we'll do from SciPy optimized. We'll import root. Make sure to run that. Run everything all the way down. And now we will do root, our function, and an initial guess. For our initial guess, I'll do maybe 380 degrees Kelvin and 380 degrees Kelvin, and we will do, how do I get this to go? We'll scroll down. 380 degrees Kelvin, and we'll do, let's try half a meter cubed for the volume. And let's run this. Wait for it to run. Seem to be having a small issue here. I'm not sure why. We have no other tabs open. Let me see if I try closing this. And there we go. That just took a second. We had to figure out what I was going to do. And we got a message that the solution converged. And down here, this is our solution. So to get our desired final pressure and desired moles of water vapor, we need a temperature of about 366 Kelvin and a volume of 0.012 meters cubed, or about 12 liters.